Good morning and good afternoon. Welcome to our 21st Build Your Simulation CFD IQ session. Today myself and Todd are going to be talking about meshes in CFD, and I guess a little bit between kind of setting up meshes, the basics, and a little more kind of like on the advanced side. But we'll get into that as we go. The slide deck and also one of the tutorials that we're going to run through is available to download at the link at the bottom of the screen. There are a couple of instructional slides along the way, so if you have CFD open and you want to grab the file and work alongside me, feel free. So with meshing, there's a few questions that I generally recommend we ask before we press solve. Does the mesh look like the real world or the CAD model? So this is assuming we've meshed the model before we started to run it. Are there 4 or 5 elements through any small kind of narrow channel? Are fans, blowers and resistances adequately meshed? And is the model mesh independent? Generally this takes a few solves to establish, but it's an important factor if we're running a final kind of study that we want to be very, very accurate. So we're going to be visiting a couple of areas in CFD. One of them is the mesh controls. I'm going to run through a small section, and then Todd's going to take over and talk about the advanced tab. And then I'll take over and we'll talk again about solver controls, but just the meshing kind of side of the solver controls. And again, if you've got CFD open, feel free to grab the example from the link at the bottom. Okay, so looking at mesh controls, I guess the first thing to think about, like I said, is does the mesh represent the geometry? So there's 2 examples here. The top one, they're the same CAD model. The top one obviously is meshed very, very coarsely. The wheels aren't cylindrical. The car isn't at all smooth. And we can see that the pressure contours along the side of the car are pretty linear. They're not kind of nicely, there's no nice gradients like we would expect. And then if we look at the air as well, we can see that there's lines in the air where the pressure result or velocity result changes, and that's driven by the edges of the elements. If we take a look at the bottom image, the transitions are much smoother, and this is kind of what we are aiming for. One comment I guess I would make is if you look at the front of the front wheel and the region in the air behind the car, here again, because the flow gets more complicated and turbulent and there's a lot more kind of happening in a smaller space, the results look a little bit jagged. So the mesh in these regions probably needs to be a little bit finer still. So the next thing to look at, I think, is mesh through narrow channels. So this might be gaps. So gaps between heat sink fins, or if we go back to the car, maybe the gap between the underside of the car and the floor. And there's a couple of examples again. So on the left we've got what I would say is a poor mesh. We haven't got 4 or 5 elements from one side to the other. This is discounting the boundary layer, by the way. So really we have maybe 1 or 2. The boundary layer, which should generally be pretty thin, is massive here and it's taking over the entire mesh. If we take a look on the right, the mesh there is going to be really good. I expect that's probably a little bit over meshed, but it would give us a good result. And you can see there's a very thin boundary layer again, which is great. Todd's going to cover this in more detail in a bit, but if I'd recommend utilizing surface and gap refinement within the meshing dialog. If we enable gap refinement, CFD will look at any gap in the model, and we can say, you know, if there's a gap between 2 solid parts, ensure that CFD has this many elements here. And we found from experience that 3 gap elements seems to be pretty optimum. We've tested more, so 4 and 5, but generally what we find is that the mesh count increases exponentially, I guess, and the results don't really change too much. So we have humongous run times for no real gain. So we recommend 3 gap elements if we're using that approach. Think about thin solid element. Sorry, Todd.
Yeah, can I bump in there and just throw in a little bit more? So an extra thing to think about is how your flow profile is going to be. So like the difference between air flowing through something and water flowing through something, there may be a very different boundary layer effect as far as how steep the gradients are going to be. So sometimes you will need to have a thicker boundary layer to capture some of those things. And then you may need more elements than the three. You know, that'll happen a lot of times when you have a very viscous fluid, you know, if we're dealing with an oil or something like that. Just as, does that make sense?
Good point.
John?
Good point.
Yeah.
Yeah, that does. And I guess the Y plus comes into play a little bit, which we'll mention later too.
Right.
Yeah, thanks, Todd. That's cool. Okay, so I guess like the nice kind of tip I would always recommend is to just kind of eyeball the model and make sure that through small gaps that you know are critical, you can see, you know, a good 4 or 5 elements, then you can feel pretty kind of safe and secure that you've got a good result. On the bottom right here, we've just done basically, we've automatically meshed the model on the left-hand side, and you can see the mesh is very coarse. It's too coarse. On the right, we've enabled, I think, 2 or 3 fluid gap elements, and we can see that the mesh is improved. Honestly, it's still a little bit coarse. Maybe we've only got 2 elements across the width there, and 1 kind of node in the center of the gap. So really, we need at least 3 as a minimum, but 4 or 5 is a good kind of place to aim for.
Shoot for more elements. If you fall short, you should still be getting decent results.
That's very true. So just a little bit about how to refine the mesh. I think a lot of people just kind of blanket refine the mesh, and that can be fine, but it might mean that we're refining regions that we don't need to refine, so we're increasing the runtime and we're not actually gaining anything. So have a think about how the flow is likely to behave and control the mesh, you know, more in kind of localized regions. You know, if you know there's a jet in the model, or if you know there's a region where the velocity changes rapidly or something happens, utilize a meshing region or refine the local surfaces or edges to give you more mesh around that area. Utilize the surface and gap refinement almost always now. I think you probably agree, Todd. I at least always have surface refinement on, and more often than not gap refinement as well. But you've got to remember that gap refinement will default to 1 gap element in the advanced box that Todd will show you shortly. Ideally, we want to change that to 3 as a minimum. And Todd's going to talk about
why that's that's an interesting default to me, because I had to modify it every time I'm going to use it. Oh, weird. Anyway.
Yeah, something for the idea station, Todd. I recommend you post something on there about it. Yeah, I think you also, Todd, are going to talk about volume growth rate. And then we're going to look at, so once you've run your model, so you've looked at your mesh and it's good, you've got some results and you think they're good, I'd recommend running a mesh sensitivity study, which we'll look at in a second too. There's a couple of different ways of doing that, but what we want to ensure is that if we increase the mesh density, so we're making the elements smaller and smaller, the results shouldn't change too much. If they change a lot, then we know that the results were very much dependent on the mesh size. So we're going to keep kind of doing that process until nothing happens. And we'll talk about that in more detail shortly. So I just wanted to show a couple of images that basically demonstrate this effect. On the left, we've got what is basically an automatic mesh. It's pretty good. But on the right, we've got a refined mesh. So you can see it's meshed a little intelligently. On the right, just around where the poppet is, you can see there's some pretty small gaps where the mesh gets finer and finer. And I've given you the pressure drop results between each two. So, I mean, the result is nearly half when we have a good mesh compared to the poor mesh.
Yeah.
So we can very safely say that the results were very, very mesh dependent. Okay, at this point I'm going to hand over to Todd, who's going to take you through some more of the meshing functions.
Yep. So this is kind of just to give you guys a very basic run through of, you know, what everything is, because I know this is confusing to a lot of people. So, you know, if we're looking across the ribbon, automatic and manual, yes, manual mesh, you specify an element size, pretty straightforward. But if we're doing an auto size, I want people to actually kind of know what the actual software is doing in the background. So when you're hitting this auto size button, it's actually going to follow the rules that are set in the Advanced tab. And these aren't too bad as the relative default, but I think a lot of people have seen that when you're running a model, you end up doing something where you're refining this part or that part anyway. These are going to be global changes. It's basically specifying a macro to run through and mesh everything. So the resolution factor, really that's like selecting a volume and tightening the mesh over here. If you're going to change the edge growth rate, again, that's how large an element can be compared to the element next to it. The minimum points on edge is just stating that, you know, if we're the smallest edge in the model, I want to have, you know, default is 2. You could force it to be more. I've seen people use that in the AC industry a lot, where, you know, you have these really long edges, and I guess that's more of the points on longest edge, because you want to have 10, 20 elements from floor to ceiling.
Hey, Todd.
Yep.
Cool. I'm glad I wasn't sure if you could hear me. Just to add something, the edge growth rate, the 1.1 there means that adjacent elements can be no more than 10% larger in size than each other. If we wanted to improve the mesh quality, we might drop that to, say, 1.05, which means that then if we refine a mesh and we spread it out by using spread changes, the adjacent elements can be no more than 5% different in size.
Right. And then relative, same thing if you're using the volume growth rate. You know, that's saying that elements can grow by 35% as we're moving away from the element that's going to be on a surface. And then we have our surface refinement and gap refinement. If I turned these on, which I need to auto size first. If I turn these guys on, then I can go into my advanced and change these parameters as well. So you can either change what your surface growth rate is going to be. Again, that's a 20% difference, and then how fast your enhancement can grow as well. Like if you do a pipe, you'll see that the enhancement actually comes in towards the middle of the pipe when it gets away from the edges. When we're using the gap refinement, one thing that I don't think we really hit on, you know, I try to use this in a lot of cases, and sometimes it won't work. If you have, you know, again, a pipe, something like that, where there's a curvature edge, it doesn't look at those as being a gap necessarily. They have to be two separate solid surfaces. And then, as John said, here's where we would change the number of gap elements, or if it's a thin solid that we wanted to make sure we had a midpoint node for heat generation, that's where we can put that in. And then using this slider, this is actually this dimension in your geometry units from up in the design study bar. Then to describe a little bit more about, you know, how the mesher works, I think this is something that a lot of people don't really have a good grasp of. If you go into the diagnostics, sometimes you'll have these little edges that are highlighted in the model, and maybe you care about them, maybe you don't. So right now I have it set so that my minimum refinement length doesn't capture the height of my little chip on a board, or, you know, it's really just two boxes put on top of each other. That means that this edge will not be considered for my meshing rules where I'm trying to get the two elements on it and then grow away from there. It'll just make sure that there's enough mesh to capture all of the surfaces. So we go from first having all of our edges, then we grow into building our surfaces, and then, you know, if we could have any kind of meshing error from if a surface is missing or can't be meshed, has some sort of intersecting surface, something like that. Then we'll go into volume meshing. The beginning of volume meshing is where we put in our enhancement layers for all of our wetted surfaces. So if you fail right in the beginning of volume meshing, or it hangs in volume meshing, typically that means that we have a problem with our enhancement layers, either overlapping or not being able to wrap around some kind of corner. And you can always change your minimum refinement length so that you can capture those surfaces. And I actually meshed this model with the minimum refinement length being captured and without it being captured. Other thing that's worth noting is you can see small surfaces that are possibly sliver surfaces for a model. Just because they're there doesn't mean that the model can't mesh. This mesh is fine. I will show you, I mean, you can see how the auto size is here. If I modify the minimum refinement length so that it actually does capture those edges, use highlighted length, it says, hey, you're going to need to re-auto size. Yep, I know. And then if I auto size it again, I get a substantially tighter mesh on that little chip. And I actually meshed this for you guys. Let me bring this guy up so I could show you. Of course I didn't update my image. Is it going to let me? Probably easier if I zoom into it a little bit so you guys can see. That bright green hurts my eyes. So I'll actually just flip this over so it's a better color. And here we can actually see, of course it doesn't do it for both of them. But the mesh is actually tighter in that second one. And then we grow away, and you can see how we have large elements on the far sides versus the tight elements on the chip. It's not as big of a difference as I would have thought, but you can see how black it is in those corners. And that's just because we have a much tighter mesh specified based on the same macro being run. I will pass it back to John unless you want me to show anything else. Did I miss anything in the dialogues there that you'd really want me to bounce into, John?
I think you answered this actually, but can you describe what a thin solid element is?
Okay, so this actually would be the perfect example if this is a chip on a board and I knew that I needed to have a heat generation on it. I actually want to have a midpoint node so that I can have my heat generation start from inside the part and then it will conduct properly to the outside. So making sure that you have at least one node in the middle of your thin solid element instead of just surface to surface. That is definitely a desired effect when you're doing heat transfer. That's not something that we need the 3 to 5 elements on, but when you have that solid, you want to have, if we're going from the bottom surface up to the top surface, make sure that there is an element in there, and you can specify what that size is in that advanced dialog. Other thing that I guess might be worth noting is the suppress. If you don't have heat transfer in something, you should always suppress it. All of the surfaces will still be accounted for. I can run a quick model if anybody wanted to see it, but essentially you're just looking at a cutout in the model so that flow would be forced to go around that part when it's suppressed from our meshing. It's not like suppressing back in CAD where you're not going to have that part available. If you wanted to do something like that, you could actually just turn the material into your fluid, like in air or water volume, and then it would be a localized mesh enhancement region.
I guess a good example of that is what we're going to show in a minute with a car model, but any kind of external aerodynamics model, you just don't need to mesh the part, right? You can even still get all the wall forces and everything from the internal of the fluid rather than the solid.
Yeah, I guess in the process, basically everything that you need to do for refining mesh can be done with selecting a volume, a surface, or an edge, using this slider, or using regions. I would suggest that that's a good way to start if you're just getting up and rolling with CFD. I think a lot of people are confused by the spread changes. Because right now I selected my surface, I tighten the mesh, I say apply the changes. when I hit the spread changes, that means it's going to run the macro to grow the elements away from the change that I made. Just to throw that in as an extra tidbit.
Using that 10% rule right now, right? Because you've got 1.1 set.
Right.
Okay.
Yeah, I didn't modify any of those.
Cool.
But yeah, everything that you do in the advanced is a global change. If you want to make something more specific because you know that's an important part of the model, you should do it with volume, surfaces, and edges. Sometimes if there's nothing around, using a region can help. Because you can always specify, yeah, there's actually nothing happening in one of our back corners. Of course, I missed. And I can get the mesh size over there and tighten this if I needed to. All right. I think I can pass it back to John. I think you've got another example to go, and then, or if you have any questions. Yeah.
You know what's funny is that you can tell who's used CFD for a long time because both you and I'm trying to break this habit today actually, but both you and I press spacebar twice to get the decision center.
Yeah.
Yeah.
I really struggle to use that tab. I've done it like 4 times. I'm proud of that.
No, I'm going to do it in a minute. You'll see. It's going to be amazing.
It's going to be amazing.
I know it's been there for a year, maybe 2, but still. Okay. So what I want to look at is running a mesh sensitivity study. The most important thing, I guess, to mention, and I think probably nobody I've ever seen use it does, is to start with a good mesh. So starting with the automatic mesh is fine, but it's much better to mesh the model a little intelligently like we did before and like Todd just talked about, so refine the areas where you know there's kind of action taking place and then turn on the mesh adaption. So there's an example in the top right of the automated process. It's kind of like option 1. It can be a little lengthy, honestly, because you need to run every single cycle to convergence. But there's so many parameters you can give CFD to optimize on that it's really powerful. The other process, which I use so often, I guess, is a manual process. And I thought what I'd do is just describe it and then run through it really quickly. So what I would normally do is mesh the model as I think it should be, based on however many years of experience, and then capture the most important results that I have. So it might be measuring the temperature on a chair, it might be measuring the pressure at a certain point or velocity, whatever's really important to yourself, and then refine the mesh by about 30% and compare the results between the two. And if with a 30% mesh refinement the results have changed by less than 5%, we can be pretty confident that our results are independent of the mesh. If the results have changed by more, depending on how much, you're probably getting closer, but refine the mesh again. And keep doing that process until you kind of achieve a nice mesh. So what I thought I'd do is just kind of show on screen for anyone that has the model open. This is actually just a tutorial model. The tutorial's in 2016 on a different place. I thought I'd share here so they're in users public now. You could pick your CAD system and open the car model. I'm going to run through it really quickly, but you know it's there if anyone would like to try. So what I normally do, just as an example, I guess, is automatically size the mesh and run the model, and then right-click on the scenario and clone it, and give it like a 30% refinement. So that's refining the mesh here within the box Todd just talked about to 0.7. Apply changes, spread changes for what it's worth. In this case, it's not worth so much, I guess. In my example, I did the same again, and I turned on surface and gap refinement, and I set 3 fluid gap elements like I explained before, and then I ran the 3 scenarios. And then I added a results point, and then I compared the different scenarios side by side. So what I thought I would do is just bring up CFD to show that. I think my screen's showing CFD, Todd. Let me know if it...
you bounced back to PowerPoint again.
Yeah,
there we go.
Yeah, cool. Cool. I'm using too many monitors and my mouse is on the wrong one. Okay, so we've got the 3 different scenarios here on the left, so different types of meshes. And you know, we can take a look at the mesh like this, but what really nice comparison, and I'm going to do it. I'm going to press the decision center button at the top,
Oh,
and
new
here,
age.
I know, I can't believe I remembered. And all we can do is compare the meshes side by side now. So we've got on the left-hand side the auto mesh. So this is underneath the car. If we zoom out a little, you can see. And the second mesh is a little better. And then the third mesh on the right is just the second mesh with surface and gap refinement turned on. So you can see the difference that the automatic process makes for you. I've not done anything else other than turn that on and go. And I thought the important point to share is the actual results. So if I added a point underneath the car, and if anyone needs me to show you how to do that, I can. But if we say pick velocity magnitude as an example and plot the velocity at this point under the car, what you'll see is that the refined mesh is really, really different. And the important thing this raised for me, I guess, is that the first two results, even though there's 30% more mesh in the middle compared to the left, the results are really similar. And the reason for that is both meshes are bad. So this is why I would always say start with a good mesh. So use some intelligence, refine the mesh where you know you need it, and then adapt the mesh from there. And then you should be kind of moving to some good results. Think that all makes sense, Todd?
Yeah, I got a question here that I'm not sure if I understand. We'll see if you grasp it. Is there any provision by doing mesh adaptation by defining a region? So I don't.
You might want to, I guess, frame the question a little better if you've got time. But I guess what I kind of think that means is, can you use meshing regions up front and then adapt the mesh from there? And I think that's what it means. And yeah, you can, right? I mean, you can use meshing regions and any technique you want, I guess, to achieve that initial mesh. And that will be treated as the mesh that CFD then kind of moves forward with as it adapts. Yeah. It's a good question, I think. Okay. So moving back to my PowerPoint, I just wanted to reiterate this fact, and I put it at the top, start with a good mesh. So do refine the mesh first, use a little intelligence, and that's a good starting point. I see the next question asking about Y+, and I'm going to cover that in a second, but I guess, yes, it is important to see within the adaptation window that we can adapt on Y+. So generally we want to set a maximum value here, and we can ask CFD to adapt on it, and it will adapt until the Y+ is below that value. I'll explain why that's important in a couple of slides' time. So just to kind of summarize those meshing points, we want to make sure there's 4 or 5 elements. Well, I guess the first thing, make sure it looks like your real world or CAD model. If it doesn't, obviously you need to improve it. Make sure there's 4 or 5 elements to any narrow channel. If you're going to use the automatic settings, start with 3 gap elements. If you've got flans, blowers or resistances in the model, make sure that they have a uniform mesh and they have 4 or 5 elements to their thickness. This is so often the reason why resistances and fans aren't giving the values that we're kind of expecting of them. It's almost always down to the mesh. And then once you've got some results, try to make sure they're mesh independent. So if you can and you've got time to kind of iterate and refine the mesh, it's a really good idea to do so.
John, we've got a question can you explain the Y+ part of the mesh sensitivity study?
I knew you weren't listening, Todd. I saw that question and I half answered it.
Oh.
And I said I will. And I promised that I will on the next slide. Yeah, I will.
You're doing that portion of it? Okay. I was like, I didn't. Yeah, I was doing two other questions and I missed that. But yeah.
So yeah, going back, so that within the box, yes, we can control the Y+ value, and this is a maximum value, and CFD is going to adapt to below that value. And the reason why, I guess, is almost as follows. I first want to kind of explain how you turn it on and how you see what the Y+ is, but there's also another value that's important. So there's 2 things. Under result quantities, and I'll bring CFD up really quickly just to explain. Under setup, solve, result quantities, we can turn different values on here. I generally have Mach number on, but the 2 I'm talking about that are important, I think, are wall mod or Y+, and stream function. And once you've enabled those, CFD will automatically plot them for you. If you've already got results and you want to add them in, just run for another, well, run again, but set the iterations to 0, and CFD won't run, it will just add these values back in. Okay, so back to the PowerPoint. Once you've enabled both of those, we need to know what to do with them. So the stream function will enable us to plot nodal aspect ratio as a result quantity, and I'll show you how to do that in a second. If I show this image, basically it's a low nodal aspect ratio is, or as we get towards 1, our elements are equilateral in size, so it's a ratio of the longest edge over the shortest edge of any element. So with the low nodal aspect ratio is like a uniform mesh, and that's ideal. The higher the nodal aspect ratio gets, the longer and skewed the elements become, and the less happy your results are going to be.
Happy results,
so,
I like it.
Me too, but I don't like unhappy results. So just to kind of measure the global mesh quality, what I generally, or we generally recommend is to keep the nodal aspect ratio beneath about 100 to 150. I'll show you in a minute how to use an ISO surface to establish whether you've achieved that or not. We can have nodal aspect ratios of higher than 150. That can be okay as long as they're away from areas of interest. It will probably slow the model down, but it is okay to have that. It's not going to kill your model, but it's ideal to have them below 150. And it's also going to have an impact on how many elements you can mesh. So the better the nodal aspect ratio, so the closer to 1 you get that, the more elements you're going to be able to mesh for the amount of RAM that you have. And there's a couple of rules of thumb there. So we generally say that, you know, if we had a perfect mesh everywhere, we might need 1 GB of RAM for every 1,000,000 elements. And that would increase up to 2.5 GB for 1,000,000 elements as the nodal aspect ratio gets worse. Now I'm going to try and tackle the Y plus value subject, which is a little difficult to explain, I think. What I've done is a link to a page on AKN, which I think is a nice kind of reference. So if you do want to kind of read up on it more, please do so there. But the Y plus is basically, it's important because it controls a distance in the boundary layer from the wall to the top of the first element. And that value needs to be different depending on the turbulence model that we use. So this is why within the adaptation we refine to different values. So for K epsilon, which is the default model, we would refine, we want the Y plus value to be between 35 and 300. We don't want it to be smaller than that because the K epsilon model has its own Wolf function and it needs quite a large boundary layer, which is why we automatically adapt to 300. If we say move to the SST model, which is still fairly new, I guess it's been around for a couple of years in our software, and it can give better, say, pressure drop results and heat transfer results sometimes. A lot of people are using it, but a lot of people aren't kind of making sure that their Y plus is beneath about 1. Maybe 2 is okay, but 1 is a really good goal. So if I kind of go back up a few screens and we were running SST and an automatic mesh sensitivity study or mesh adaptation process, we'd want this value here, the max Y plus, to be 1. I should use my mouse on the other screen. There. Okay, so what I thought I'd do is just kind of show you how to plot both of these things. Well, I guess plotting one of them is an easy enough thing. They're both basically the same. So in my model, I have done exactly what I said, so I've enabled those things and I ran it. And what I'm going to do is add an ISO surface. And over here on the right, we can plot Y plus. So we can capture our Y plus value, which here, because my mesh is pretty bad, is huge. But more importantly, we can plot our nodal aspect ratio. It's going to give us a scale, and we can see that on the left here, my nodal aspect ratio goes from 1, which is obviously the minimum, the perfect element, to 123. So, you know, the mesh is actually pretty okay. And what we can see is that the kind of more perfect elements are spread out through the fluid. And as we kind of try and find the more skewed elements, they're within the boundary layer on the floor and underneath the car here. And we can right-click and show the mesh on these two if we want to. So you can see that they're pretty kind of long and thin elements. Okay. I think that covers everything I actually wanted to show. Does anybody have any questions, or do you have anything to add, Todd?
Trying to think here. I think you did a good job with the, just to throw out for a little bit more reference, it would be good for people to look at actually what the turbulence models are doing. Like the big difference between SST and K epsilon is kind of the wall function that's happening in the enhancement layers. Just kind of reading over that in the help might give a little bit more understanding for where that Y plus value is the most important. Because you'll see a much bigger effect coming from a SST turbulence model. Does that make sense, John? Silence.
And how long was I talking to myself for? Just
yes, there he is.
And the other important thing to bear in mind is if you are running the SST turbulence model, we need that small y plus value, and we normally do that by changing the mesh enhancement, right? There's a really nice webinar on this if you look up turbulence models. Royce talked about it, but we would basically increase the number of layers and change the layer gradation generally as well. I've got some rules of thumb that I always send out if people ask about this, and if you look on Google or our AKN site, it's all there as well. But a value of somewhere around here is a kind of good starting point. Okay, I can see one other question that I guess we haven't answered really. Do we have any specific advice for meshing in a compressible flow analysis? Only really what we've already said, I guess. I mean, with compressible models, you might have regions where the density and temperature change really quickly, or you might have shock waves. And again, those are the regions where you're going to want the most mesh. I'm running one right now, and CFD's adapting really nicely, and it's capturing these kind of rapid density changes really well automatically. So yeah, just start with a good mesh. Be mindful of where those big changes are going to happen, and I guess that would be my answer. How about you, Todd?
Yeah, the most awkward thing with a compressible model, I would say, is that some of those shock waves and things like that aren't necessarily intuitive right off the bat for when you're running it. So, adaptation can help a lot with that because you will get this larger gradient there. But yeah, it's not always necessarily the most intuitive thing for where that pops up, and it can be a tricky thing by all means, but that's what you're shooting to capture.
Yeah, do the obvious as well, do the mesh refinement study, even if it's manual, just to be really, really sure that you've kind of captured everything properly.
Right.
There's two more questions. So one, are there any specific scenarios where we might use KE versus the SST model? I guess like the SST model can be really nice when we can't quite capture the pressure drop as well as we want to. Honestly, that often comes down to the wrong Y plus value being used with the KE model. If you refine the mesh too much, the Y plus is going to be incorrect. But with things like cyclones, or I guess like hot and cold plates where you've got a lot of heat transfer, so SST is really nice at kind of capturing a thermal boundary layer versus the standard kind of flow boundary layer. So that might be a really nice application. And significant results differences.
Extra 2 cents there. So I always prefer, if I can get close enough with less tweaks, to use the less tweaks, because it's less that I can have an error that's going to show up in my design process. If you're using SST and all of a sudden you forgot to change one of your designs to SST, your K-epsilon results may skew you in the better direction, and it's actually error that you're choosing the wrong design. My extra take on it.
Cool. Yeah, that's cool. Okay. I'm trying to type and talk at the same time.
Right.
A little off topic, I guess, but are there any significant result differences from ADV1 to ADV5? Possibly. Yeah. I mean, I think if your model is, say, compressible, you'd always want to use advection scheme 2 or 5.
Right.
It's hard to really kind of
You'll
quantify the
definitely
differences.
do better. I mean, ADV5 is the one that I actually lean away from. You know, that's probably my most constant change. It gets me every time when somebody's complaining about result without knowing that I did it, because it's an automatic click for me. But really, yeah, that's a big So there are the times that you really need to do it when you're doing a free surface. I've seen some people need to use it for scalar analyses as well when you're really not having any of that scalar mixing, because it'll make it less diffusive. So it can help out in that scenario. You can put in 1e to the -9, but leaving it as ADV1 can also kind of skew that in that direction for you. But most of the time I'm using ADV5 unless something's going wrong. Or it's pipe flow, because ADV4 does it easy.
There's a couple of other points too, I guess, which are noted just at the bottom. I guess they almost should be at the top, but if we're using resistances, if they're volumetric resistances, we want to use ADV5. If we have surface resistances, we want to use ADV1. I guess that's the one that kind of catches people the most, I would think.
Yeah, and I don't know, I'd need to restudy that. I haven't played enough with that to really know. Because so this is a fun thing to talk about since you brought that up, John. The point of using a surface resistance, you can substantially reduce how much mesh is required for the resistance. And that's because we want to have the ability to look at a node out in the fluid, you know, towards the resistance. Then we want to look and make sure that if we've got a specified pressure drop that's supposed to be happening from that resistance, as we go through, we want to see that that pressure drop happens. So you want to have a node inside the resistance that we can check versus a node outside. And then we want to do the same thing leaving the resistance. So you really want to have 5 nodes across a resistance, just so that that internal node isn't being used for both sides of the resistance. But when we go to using a surface resistance, we're just saying, boom, I want that pressure drop right here. Because I need it in the analysis, but I don't need to necessarily see it spread out. So if you've got a really thin resistance, you know, screen or something like that, we can capture that at just a surface instead of having this very thin volume. So what'll happen is then we just grab outside node, middle node, outside node, and we know that the pressure crossing that one element has to change. So I don't think we described the meshing requirement on resistance previously, did we?
Not sure. Not sure.
Yeah, I don't know. I actually have a hand drawn with dots to explain that fact, because I should have brought that with me. Because it's
There's plenty of articles on it now. It's all there. It's documented.
Yeah.
Thanks for that. There's 2 more questions. One of them, I think we'll just probably answer these 2, then call it a day, because they're slightly off topic, and I think that's probably how we're going to go from now. But one of them is about placing refinement regions within CAD. if you run traces through the model, they appear to be kind of broken at the interface. I would suspect that that's because the results aren't converged. I can't see why else it would happen, but you know, if you are seeing that, maybe log a case with us and we'll take a look. There's a question here that's very mesh related about we want 4 or 5 elements across the thickness of resistance. Yep, it's in the flow direction. That's right. So generally through the thickness, but yet in the direction of the flow. So the direction we're going to see the kind of largest pressure drop. Absolutely.
Right.
What I normally do is just give the whole part a uniform mesh, and normally the thinnest section is where the flow is going. Not always, but normally, and that has the 4 to 5 elements. And the last question I think we'll answer is, in many cases for me, passive cooling, higher power electronics at 10% rule is this kind of acceptable margin for convergence. Can we get more accurate than 10%? I'd say yeah. If you really wanted to, and you set the model up, and you're representing reality, and you're kind of comparing apples to test, sure. I think that's entirely possible.
Yeah.
Do you agree, Todd?
Absolutely. I mean, I've definitely gotten models to be in 2 to 3%, and then some people are unhappy with that, and they want to get it within 1, and that's when you start to get into this is numerical modeling.
Yeah.
But sometimes I can hit it, so it's possible.
Yeah, I agree. It is possible, but you've got to kind of decide whether the kind of meshing refinement trade-off is what you need. So often we might kind of go on that 10% rule and optimize our design and compare lots of things side by side. Then when we've got our final design that we know is the kind of operates in the best way we want, maybe then we'll refine the mesh and figure out exactly what the real kind of answer is going to be.
Yeah, the thing that comes to mind there is the actually wrote this in an email earlier. 80-20 rule. You can get 80% of the answer with 20% of the effort. When you want to get the last 20% of the answer, it's going to take 80% more effort. So be aware of how much you're going to put in to get. If it's going to take you an extra 2 days of runtime to improve by 3% of error, it's just getting exponentially harder to improve that result. So you don't want to do that on all of your runs, or you're not going to run as many designs. That kind of makes sense, John?
Yep.
Did you leave
that's exactly my thought.
Oh, all right.
No, I'm here. I mean, I think that's generally what we do, right? We kind of optimize the design. We use CFD normally up front in the process. We optimize our design, and then we kind of really refine the model for the last one. Yeah.
Right.
Absolutely.
100% off topic, but when you're doing the electronics natural convection, same thing with radiation. Because it takes so much longer to solve, I'm going to run as few of those as I can. I'm going to do my baseline test, and then I'm going to benchmark everything without radiation, and then when I have the design I chose, I'm going to run radiation again just to make sure, but as few runs as I can with that. So if I don't have to run a model that's going to take a week, I'm not going to.
That was 100% off topic. Well done, Todd. I suspect James might cover that section anyway. Okay, I think that captures everything we wanted to share, and we've answered all the questions that came in. So bid everyone a happy day.
Appreciate everyone's time. Yeah, thanks for coming.
See you next time.